The term we're going to be seeing quite often in this chapter is carrying capacity. And carrying capacity is the limit to how high a population can grow. So here it's represented, this carrying capacity of this fish population size reaches a certain point. And different factors that could affect carrying capacity could be, with the fish, limited dissolved oxygen, low food availability, disease, predation, and limited space. Well, there's another thing looking at the minimum amount of individuals you can have as well. And the minimum viable population is the minimum number of individuals needed to support a breeding population, and this can affect the rate of the growth. And individuals may not be able to locate mates if the population is too small. Interbreeding may produce weak offspring, so reproducing with siblings. You can have low genetic diversity for adaptation, can lead to extinction. And there's a great example in Orlando that you can see this. Yeah, Lake Eola. Have you ever been to Lake Eola? The example here at Lake Eola is the swans. And if you've ever stopped and looked at the swans, some of them you can see genetic mutations. And in some individuals you can just tell they just look fragile or weak. Well, there are not that many swans at Lake Eola. It's a very condensed area, and those swans do not have the option to be able to breed with many individuals. They just have a low population size. So when you have that low population size, you tend to have interbreeding, breeding with siblings or individuals that are genetically similar to you. And over time that can produce weak offspring and create low genetic diversity, which can lead to extinction. When we look at population growth, we have two different types of curves that we commonly see. We have the J-shaped curve here, which looks like this exponential growth, and then the S-shaped curve, where it's already had its exponential growth and it's hit this dotted line to where it cannot go past. And what's that called? Yeah, that's called the carrying capacity. I'll represent C by capacity here. So the carrying capacity here is that dotted line. So when a population reaches it, it cannot go past it. It tends to plateau and then either drop off or stay at that plateau. And if we look more detail at the S-shaped curve, you have these different periods within it. You have the lag period, and then you have the exponential growth period, and then the stable equilibrium where individuals have reached that point, that carrying capacity. So if we look at the human population and how it's grown over the last 2 to 5 million years, and then takes a big jump to the last 10,000 years, just look at this. I mean, the last 10,000 years, the population growth tend to be linear or grows in a straight line, not much exponential growth. But look what's happened over the last 150 years. How the population has grown so dramatically to about, we're right here at 7 billion people at this time. Where do you think that the population is going to go to? 2025? Do you think it's going to be at 8 billion? 2050? Do you think it's going to be at 9 billion? Do you think it's going to hit that, be able to get that high? Humans have been the only species that has been able to continuously increase their carrying capacity. Here, let's look at the population growth and look at some historical references within the population growth. So going back again 500,000 years with the human population, you can see hunter-gatherers, cave art. Here at 8,000 you have the agricultural revolution, tends to still increase linear, metalworking, irrigation. We have the Christian era here. Population tends to increase a little bit here. Have this little dip. What do you think that little dip is? That's the Black Plague that came along. And then industrial era starts about here. Get that exponential growth. With the human population growth, we have interactions that affect the carrying capacity, availability to raw materials, availability to energy. waste disposal, and interaction with other organisms.